everyone. In the previous class, we discussed about the parameters of Moore-Coulomb failure criterion and Hook and Brown failure criterion. We saw that how the parameters of Hook and Brown criterion can be used for the determination of Moore-Coulomb parameters for the rock mass under effective stress conditions. Then we had some discussion on the deformation modulus along with the disturbance factor. Today we will learn about few failure criteria which are applicable in case of the rock masses. The first one includes the failure criterion for the rock mass when the rock mass has single plane of weakness. This is also called as single plane of weakness theory. Then we will discuss about the Barton's theory to determine the rock wall strength. So, to start with, let us have a look at this slide where you have a figure which is representing the rock mass having a single joint which is inclined at an angle beta to the major principal plane, and here the sigma 1 is the major principal stress and sigma 3 is the minor principal stress. So, on this plane your major principal stress is acting, and from this plane only we are taking the orientation of this discontinuity which we are representing by beta. I want you to remember this fact that how the orientation of this joint, which is this joint, is being measured, because all our plots, all our result will be depending upon this value of beta and how it is measured. So, this part represents the intact rock portion, and this is what is a joint, and you know that when there is a presence of joint in the intact rock, we call it as rock mass. The condition here is that you have only one plane of weakness. So, the theory that we are going to discuss is also called as single plane of weakness theory. What happens when there is an introduction of an discontinuity plane in the intact rock? Overall strength characteristic of the rock mass reduces as compared to the intact rock. So, here in this figure the plot for the intact rock and the joint has been shown in the space shear strength tau f and normal stress sigma. I do not need to explain you this now, that obviously intact rock will have much larger strength as compared to that of the joint, and this would result in the lower value of cohesion and the friction angle in case of the joints. What does that mean is that Cj is less than Ci and phi j is less than phi I. As it is evident evident also from these two straight lines. In case if we have a state of stress, you know that that can be represented with the help of a Mohr circle. So, let us say that there is a point or the state of stress which has been represented by this point A in tau sigma space, then this will have its coordinate as sigma j tau j, where sigma 1 and sigma 3, these are major and minor principal stress. Because here this is giving us the state of stress at failure. So, you all know that by the property of the Mohr circle, if we join this with the center, the angle that it subtends gives us that plane of the discontinuity. That is, half of this angle is going to give us the orientation of the plane of discontinuity with respect to the direction of this sigma 1, that is direction of the plane on which this sigma 1 is acting, which was horizontal in this case. Now, shear and normal stresses at discontinuity planes, which are represented by point A, can be given as sigma j is equal to sigma 3 plus sigma 1 minus sigma 3 upon 2, 1 plus cos of 2 beta. We have already discussed this or derived this with respect to the Coulomb-Navier failure criterion, but the same way you can use these trigonometry principles and can derive these. So, I am not repeating it here. And then tau j is equal to sigma 1 minus sigma 3 upon 2 into sine of 2 beta. So, this is how the state of stress which was represented by the point A can be given in terms of sigma 1, sigma 3 and beta. For the failure to take place along the joint, these two stresses should satisfy the Mohr Coulomb failure envelope, which is given as tau j equal to Cj plus sigma j tan of phi j. We just saw it in the previous slide. Now, what I will do is I will just substitute these two values in this expression and see how it looks like. So, that is going to give me this expression, which is half sigma 1 minus sigma 3 into sine of 2 beta, that is equal to Cj plus sigma 3 plus sigma 1 minus sigma 3 upon 2, 1 plus cos of 2 beta, this whole thing multiplied by tan of phi j. Just simply substitute the expression for tau j and sigma j in the Mohr Coulomb envelope for the joints. If you solve this or simplify this, the condition when the slip occurs along the joint, you will get as sigma 1 minus sigma 3 is equal to 2 times Cj plus sigma 3 tan of phi j divided by 1 minus cot of beta into tan of phi j, this multiplied by sine of 2 beta. So, if the slip has to occur along the joint, this condition should be satisfied. Now, take a look at this expression and just substitute beta equal to phi j in this case. So, say if I substitute beta equal to phi j in this case, what will happen? See here, this is cot beta and this is tan of phi j. If this beta becomes equal to phi j, what will happen? This quantity will become equal to 1, will be equal to 1 for beta equal to phi j. Once this become equal to 1, this denominator here will become equal to 0 and that would result into this sigma 1 minus sigma 3 tending to infinity. Then you take another value of beta which is equal to say 90 degree. Then just substitute that beta is equal to 90 degree. So, you take a look at this quantity which is sine of 2 beta, this will become equal to 0. So, again in this case your sigma 1 minus sigma 3, this will tend to infinity. What does this signify physically? Rock mass will not fail along the discontinuity either when this beta equal to phi j or beta equal to 90 degree, because in these two conditions the strength of the discontinuity which is given by this sigma 1 minus sigma 3 is tending to infinity. So, the failure can take place only in the intact rock. So, it is not that if in the rock mass, intact rock as well as discontinuities are there, then the rock mass will fail always along the discontinuity. It will also depend upon the orientation of that discontinuity. Rock mass may not fail along the discontinuity, but the failure can take place in the intact rock. So, that possibility can be there. So, the single plane of weakness theory gives us the idea about the range of the orientation of the discontinuities along which there will be the failure along the discontinuity. Take a look here that it is the space sigma 1 minus sigma 3 versus beta. So, if we just substitute the values of beta in the previous expression which we have derived, we have seen that when beta equal to phi j, this tends to infinity, and for beta equal to 90 degree, again this is tending to infinity. This horizontal line is giving us the strength characteristic for the intact rock. So, if beta is lying between phi j and 90 degree, the failure will take place along the discontinuity, otherwise the failure will be taking place along the intact rock. If you try to plot for the various values of beta, sigma 1 minus sigma 3 versus beta, you will see that you will get a minimum value of this strength sigma 1 minus sigma 3 at this angle, which is 45 plus phi j by 2. This can be proved graphically as well as it can be proved numerically also. like you take the differentiation of that expression sigma 1 minus sigma 3, differentiate it with respect to beta and make it equal to 0, and you will see that for beta equal to 45 plus phi j by 2, you will get the minima of that equation or this curve. Now let me explain you this all over again with the help of more circle representation. So here in this figure, there is a space of tau versus sigma, because you know that we have the more envelope in this space in the form of tau equal to c plus sigma tan phi. And here you can see that there are 3 circles in 3 different colors. One is for the intact rock, and that has been given as the black color, that is for the intact rock. The other one is red color for the joint, which is this, and the third one is blue, which is somewhere in between, so that is intermediate condition. Why do we have all these 3 and how these are going to help us in interpreting the single plane of weakness theory? Let us have a look. So first you focus on this red circle, which is represented by circle A. So you see, this is your circle A. So this is representing where you have the failure envelope for the discontinuity, and you know that for the discontinuity you are going to get the lowest strength, and that you will get at this angle, that is when you have this 2 beta w equal to 90 degree plus phi w by 2. So here I have replaced that phi which we were discussing earlier with respect to the discontinuity. I am writing it as w, that is for wall, that I am writing here as phi w. Now in this case you have the cohesion intercept as Cw. So this is going to give us the failure locus for the condition when the state of stress just reaches the discontinuity. Okay. Now you can see here that this is a point which is tangent to this equation for the discontinuity, and the angles you can see that this from this point, if you add it to the center of this circle, this angle would work out to be 2 beta w, which is equal to 90 plus phi w. So before I go to the intermediate case, let us see the other extreme which is there in terms of the intact rock. So this circle for the intact rock has been represented by this circle C, and this case the circle touches the intact rock failure locus. See, this circle is touching this envelope for intact rock at this point. So if the rock mass has not failed along the discontinuity, then there are chances that it can fail with respect to the intact rock. So in that case, to represent that state of stress, this Mohr circle will be helpful, and in that case you are going to get the highest strength. and that is why here it is written that corresponding to this circle, the failure will occur in the intact rock if it has not already done so along the discontinuity. Now take a look at the last circle, which is the circle B, which is the intermediate case. What will happen? So, first we had two extreme cases, that is the lowest strength in case of the discontinuities and the highest strength in case if the failure is taking place in the intact rock. What happens if the state of stress is somewhere in between two extremes, which is represented by circle B in this case, which is of the blue color here. Please understand this carefully, focus on this figure. This is the circle corresponding to any state of stress, which is the intermediate case between circle A and circle C. Now, from the center, we draw two lines, one joining this intersection of circle B with the discontinuity envelope at this location and another at this location. So, I have these two lines. Now, you know that any state of stress which is lying above this will signify the state of failure. If it is lying below this, that means still the rock mass has not failed along the discontinuity. Now, you see this part of the circle. This is lying above the discontinuity envelope, but well below the intact rock envelope. What does that signify? That the failure is not going to take place in the intact rock, because still the state of stress is much below the failure envelope of the intact rock, but the failure will occur along the discontinuity in this zone if the state of stress is here. Now, so this is going to give me the range of angles along which the failure can take place through the discontinuity. You have, in case if you have this line, you will have this angle. In case if you have this line, you will have this angle, this complete angle. Now, the range of this angle from here to here, which I am drawing with a solid thick line, this is the range of the angle if the discontinuity is in this range, then the failure can occur along the discontinuity. So, we had two extreme cases where one is the lowest strength, another one is the highest strength, that is corresponding to intact rock, and the lowest strength is corresponding to the strength of the discontinuity. Now, in case if you have any state of stress in between these two extreme cases, then it is not that for all the orientation of the discontinuity you are going to observe the failure along it. If you have the portion from this to this, let us say, and from this portion to this portion, no failure is going to occur, but for these ranges of the angles, failure can occur along the discontinuity for these intermediate case. So, this is what that I wanted to discuss with you, the single plane of weakness theory. Coming to the next theory, which is the Barton's theory for joint wall strength. We have had some brief discussion about this when we were discussing about the classification of the rock mass. But for the sake of completeness and some additional input, I have put this again here. So, when I talk about the joint wall strength, this refers to the compressive strength of the rock that makes up the walls of the discontinuity. Barton in 1973 introduced a term called joint wall compressive strength, which was given by JCS for the wall strength, and this was later modified by Barton and Chaube in 1977. This JCS is an important factor governing the shear strength and the deformability. In case of the unaltered joints, this JCS is equal to the UCS of the rock. Now, if we neglect the cohesion, the shear strength for the joint wall can be given by this expression, where you can see that this angle I, which is the roughness angle, that also comes into picture. So, this term is there phi b, which is defined as a basic friction angle and is approximately equal to phi r, and the roughness angle is represented by I and given by this expression, where what is this JRC is the roughness coefficient. At low values of effective normal stresses of sigma n, this I can be unrealistically large. So, for the design purpose, this quantity, that is phi b plus I, it should be limited to 50 degree, and JCS upon sigma n should be between 3 and 100. Now, the shear strength can be defined by this expression. So, what we have done is we have just substituted the expression for I here in this expression, and the resulting equation is this. Average value of phi for the rock is given as 30 degree, while the value of the roughness angle is 40 degree. Now, at very early stages of movement along the discontinuity planes, there is relatively high interlocking due to surface roughness. So, it will have a friction angle of phi plus I. We have discussed this in detail, that when the joint surface, it will have teeth, then what will happen, and when you have the large value of the normal stress, that is towards the end of the test with large value of the normal stress, these asperities are sheared off, and in that case this I reduced to 0 and phi reduced to the residual friction angle, which is phi r, and therefore the shear strength is given by this expression, which is for the large value of sigma n. Now, how to determine this JCS and JRC? See, this JCS can be determined from the Schmidt-Hammer rebound number on the joint surface, which is denoted as R. We are familiar with this figure. Here you have Schmidt hardness for L hammer, and here you have these lines are there. These correspond to various values of unit weight, and on this side, that is on this scale, you have the compressive strength of the rock surface. So, this is on the log scale. You can pick a value of R, say it is 40. So, you will have it here, let us say it is 40, and then let us say that the gamma value is 20. So, you take it this side and you will get this as the value 50 MPa. Likewise, you can take, whatever is the value of this R and whatever is the value of this unit weight, corresponding value of the compressive strength can be picked, and that would take the value of UCS. Coming to the joint wall roughness coefficient, this we did not discuss at that time. So, here this is how the joint wall roughness coefficient JRC can be determined. On this axis, you see you have the length of the profile in meter, and on this axis you have the amplitude of asperities in millimeter. Now, what do we mean by these two things? Take a look at this small figure which is here. This is the length, and over this length, whatever is the rock roughness profile, okay, you just take its amplitude at various locations. So, you see that here it is taken as A1 here and A2 here, and you can find out that what is the average amplitude of the asperities along that length. You have to choose the length in such a manner that more or less that amplitude is more or less same. In case if you have large variation in the amplitude, then you divide it into some different lengths, and corresponding to each length you obtain that average value of the amplitude. Now, if the length of the profile is, let us say, 1 meter, that is here, and say amplitude of the asperities is somewhere, say it is 1 millimeter. So, I will just take it like this and extend it. So, it is intersecting somewhere here. So, you can see that here some numbers have been given which are representing the values of JRC starting from 0.512 and it goes up to 20. So, this point is lying in between 0.5 and 1. So, you just interpolate and then you can find out that what is the value of JRC in this case. So, roughly if we take, in this case maybe it is coming out to be say 0.52 or so. So, this is how that you can determine the value of JRC. Once you know JCS, once you know JRC, substitute in that expression for the shear strength and you will be able to obtain the joint wall strength as per Barton's theory. So, just to summarize, we learnt about the single plane weakness theory and Barton's theory for joint wall strength. So, this is what that I wanted to discuss with you as far as our chapter on constitutive modeling of rocks and rock masses is concerned. So, in the next class, we will start the new chapter on the application area for these rock engineering. So, one of that or one of the major application area is the tunneling. So, we will start our discussion with respect to tunneling from the next class. Thank you very much.